So the function of photovoltaic or solar cells, that's what you have photons come in and then you have electrons out, right? And then basically when we talk about the courses, we need to figure out what are the steps or what are the mechanisms there, that convert the energy from photons to the electrons. If you think about the sunlight, that's basically made of photons, and then if you think about electricity, which is made of electrons, right? Basically, we want to convert energy from photons to electrons. Okay, just the energy from photons to electrons. That's what we need to do. So that's come to your mind. That's why the many photovoltaic devices are made of semiconductors, because the semiconductor, the electrons initially on the ground state. Under the sunlight, the electron will be promoted to excited state. And prior to excited state, that excited state called conduction band. Then the conduction band basically means electrons can conduct, can move freely. Okay, so that's what you can see here. You have photons in and the electrons out. That's basically it is. Okay. So if anyone have questions, you can ask. Feel free to ask questions. Okay. So with that, require semiconductors, right? Why it requires semiconductors? Let's see if I can get my. Uh, if you look at the electrons, right, as I just mentioned, initially they all stays on the valence band. Valence band, you know that electrons are not free, right? Not mobile. So if the sunlight, if the photons here, for example, if there's photon comes, right? Just a second. Okay, if you think about there's photons, right? Those photons comes, then promote this electron from here to there. Now this H mu, see the electron, right? Take the energy from the H mu. Now H mu is lost because it lost its energy, right? And then that electrons will promote itself from valence band to conduction band, right? Conduction band here is like a highway, right? It's like a highway for electrons, a highway. So the electron can move very fast, very quickly, okay? And then we call that electrons, we call any electrons on conduction bands, this CP conduction band, this valence band, we call that free electrons, okay? So free electron can move around and can be collected if you have what? If you have the contact here, for example, the contact or other contact here, then you can collect the electron will eventually go through here, or electrons will stay on this contact. That can be omnimoment, right? On the other side, this on valence band, whenever you have vacancy for electrons, this hole, is called free charge or free hole. This hole can move freely too. They will collect by here. So eventually you see they have electrons on the left side contact, on the holes on the right side, right contact. If you have what? If you have load here, you have load here. You see the electron will flow like this. See, and then you see you have electricity, right? Electricity flow, of course, for the positive charge, electricity will be go the opposite direction as the electron flow direction. So that's a very basic process for how a photovoltaic works. And here you can see there's a silicon solar cells, right? The silicon solar cell is the back contact. This is the back contact. Whenever the sunlight comes from the other side, so that side, the other side called front contact. Okay, this is a front contact because where you see the sunlight come, these directions. On the back side, you call that back contact. And then you can see there you generate, typically this is a p-type silicon. Under sunlight, you generate electron hole pair, and then electron is negative charge, hole is a positive charge. And then what you want the charge separation. Charge separation help you to move electron to the one contact and then hole to the other contact. You don't want this electron hole, goes random directions and then they recombine. You want to separate them. That's called charge separation. So how can you separate the charge inside the active materials? For example, p-type silicon, or in perovskite will be active perovskite, and then if a polymer solar cell, that's basically conjugate polymer, right? You can make the electron holes to transport on one directions by what? Apply electric field. Okay, that's the same thing here. For all these solar cells, you have the junctions. Inside the junctions, you have built-in electric field. That built-in electric field will help to separate the charge. If electron goes to one direction, hole goes to other direction, and then you have charge separation. Okay, so that's about the charge separation. So slides has a lot of explanations there. So here, typically, I would ask the students, if you think about in silicon, which carrier transport faster. If you think about the carrier transport faster, you look at uh, the mobility, right? You look at the mobility will be mu, right? Like mu e or mu h. Then because the velocity equal the mu equal to what? Mu equal to velocity, right? Divided by what? Electric field, right? You know that to separate the charge, we have to have electric field. Okay, now you have electric field, and then you have velocity or the speed of the charge, right? And then now you have whole electron. Whole is positive charge, electron negative charge, and then you want to figure out which one is faster. So typically electron transport much faster. That's why in solar cells we'll talk about later. You use p-type materials as the major layers to absorb the sunlight. Okay. So here, if you look at this are typical solar cells. You see, it's a silicon solar cells because it looks blue, and then there's a lot of wire here, a lot of wire here. See all these wires. See all the wires. This the contact. Right. This one is actually the you can call that just fingers. The small fingers. Okay. So that's the small fingers that collect all the charge. Then here, there's a lot of big wire that's called, this is small wires. Okay, layer wires, or that whatever you want to call that. Then here, these are thick wires. Uh, Typically, you call the small wires just the contact, and then the thick wire you call that bus, right? Because bus can hold more people, right? The same thing, this big wire can hold more electrons, so move electrons quickly. And then now, if you look at the mobility, electron has mobilities, 1400 centimeters square per V per S. If you remember that, velocity divided by the electric field, right? Velocity is what? Is centimeter per second. And the electric field is voltage per second, right? Volt per second. That's why you get the centimeter, centimeter square. Oh, I mean, voltage per centimeter, right? The electric field, right? That's how you see. It's V divided by E, right? What is V? V is what? Centimeter per second. Then E is what? The volt per what? Centimeters. That's how you see the centimeter square over V over S, okay? And then look at the whole mobility, it's only 450. See, this one is about, the electron mobility about 3 or 4 times higher than whole mobilities, okay? That's why if you look at the solar cells, you basically use p-type materials, the p-type. Because in p-type, when you have sunlight shine there, you generate electron. That electrons, will have higher mobility than the holes. That's why you use p-type materials. Then, okay, here's the definition, because later we're going to talk about the majority carriers, minority carriers, free carriers. Okay, so majority carriers basically, if you think about the silicon, if doped by your silicon, you have what? You have p-type silicon, right? P-type silicon, then n-type silicon. Okay, so p-type silicon basically is what? Is P here means positive, N means negative. That means when you dope the silicon with p-type, you have a lot of positive charge there. To make positive charge, you dope that with boron, because when you dope it, you basically remove, right? You replace the silicon atoms with dopant. So dopant, because boron has 3 electrons, then silicon has 4 electrons. When you replace silicon by boron, you bring 3 electrons, but control the silicon itself is 4. So you are short with 1 electron. That's why you dope this. When you dope the boron, you dope that as positive charge. If you dope the n-type, you use phosphorus, because phosphorus has 5 electrons, 5 valence electrons. When you replace silicon, which has 4 valence electrons, you bring 5 in, you bring 1 more electron. Kind of you give the silicon wafer one more charge. That's why you dope that n-type. Okay, this boron. This P is the boron. That P is this P means phosphorus. That M is negative charge. Okay, when the p-type, n-type, you call that positively charged or negative charge. Okay, so the definition here, whenever the silicon is doped by p-type, you know that positive charge is the majority carriers, right? When you dope with n-type, you have a lot of negative charge, so negative charge is a majority. If you identify one is majority, the other one will be minority, right? So here, if you look at this n-type semiconductors, the dopant is the majority carries electrons, so that minority carriers will be what? Will be holes, okay? Minority carriers is okay. But in the N-type, majority is electrons. In P-type, it's holes. When I talk about minority, just opposite the other one. Okay. So this is definition. The less abundant is minority carriers. And free carriers, as I just mentioned earlier, whenever you get electrons to the conduction band, that's a free carriers. Even you dope the electrons. When you dope electrons in the silicon, the doped electrons will stay on the conduction band. These are also free electrons. Okay. So here, if you think about all solar cells, is actually is diode, right? The solar cell is basically diode, but it has a photocurrent there add to the diode. So now let's understand what the diode function. The diode you have what under equilibrium. That's where if you think about the basically p-n junction is like this, right? This is the p. Okay? This is the m, right? Then this is the cb. This is a maybe I should call that energy levels. Okay, if I call that energy level C, this is EF, beam level, right? EF, and this is the EV, right? And then for P-type, the film level is closer to the EV because they don't have sufficient electrons. Their energy gets lower, right? N-type, since you dope with extra electrons, that's why EF is closer to the EC, and EV is here, okay? So under some equilibrium, since these two P and N will exchange carriers, their film level will get closer to each other, okay? And then I will use different color here, right? Color. So now this film level will move to there, you see here, like this. And then, your EC also move the same amount. EC will be here. Then your EV will move up too. EV is here. So now you have, now the film level will be aligned with each other. And then I'm going to remove that. I'm going to remove this part, old one. Okay. Okay. Now, then this is EF, this is the EV, this is the C. Then you collect this together. Now you see the p-n junctions like this shape, right? This shape. That's the same as here. See this, right? Okay. Now, when the EF on the P side, EF on the N side, they are aligned with each other, we call that under equilibrium, okay, under equilibrium. And then if the N side, for example, if you add the bias, okay, to the N side, you move the N side higher. If you move the N side, I use another, color here, let's say this color. If you move this side higher, and then you see here, you kind of move, this is what? Same color there for this. This is the EF. This is what? This is the EFIP, EFM. If we move this, there's separation between them. One is here, you see here. Okay, here. The other one is moved to there. You see the separation between EF, separation between these two now aligned, and then it's separate. And then if you move inside to the higher, and then that's called forward bias. And then if you move inside lower, that basically you add what? You think about the polarity of this the battery. You change that to here negative, here positive, and then you basically move this p side up. In other words, you drag this inside down. You see here, this one goes down, this one goes up. And then this called reverse bias, okay? Now let's take a look at these videos, okay? I'm going to stop sharing and then sharing a new one, okay? Okay, this is very basic diode structures. Can you guys see this? Okay, now let me start, okay? Basically, the diode can work under what? Equilibrium, forward bias, reverse bias, okay? And then now let's see under equilibrium, okay? Under equilibrium is this. See, there's almost no net charge flow from P side to N side or from N side to P side. There's a few atoms goes from N to P, and also meanwhile there's few, not atoms, there are few charge. There are few, positive charge from P to N. Meanwhile, there's a few, negative charge from N to P, and then they are under equilibrium, okay? There's no left charge. There's no flow of the electrons or holes, left flow, okay? And then under forward bias, now you move the inside up, you basically give the electrons a lot of energy so they can go from N to P easily, okay? Now you see, right? The left side you see all the positive charge, the right side or the negative charge, right? And then if you look at this, since you add the negative charge to the P to N side, see there's current flow, from the actually it's from N to P, right? Because this all the red bar goes from N to P and then goes to external circuit and then back to N. You see that? This I can plot it. Okay. I cannot do anything. Okay, and then that's the forward bias. You basically facilitate the extra electrons goes from N to P, right? That's basically a diode work, right? When you add forward bias, the diode is open, the current flows through there. And then if I go reverse directions, right? And then you see here, there's because under equilibrium there's no current flow, right? Reverse bias will make it even more difficult for the electrons goes from N to P because you push electrons down. Now electrons have much more barriers to go through N to P. That's why there's no current flow if you change this, polarity of the battery. Okay. Is that clear for everybody? Okay, now let me go back to my slides. Okay, this is what I just discussed. Okay, this N type or P type. Okay, so since you guys all have the slides, you can check this by yourself. Okay, and then this is under equilibrium. What you see here, the Fermi lever. See the Fermi lever here. This is EF, F. This is EFN. They are aligned. Okay, they are aligned. And then there's EI. EI is called intrinsic energy level. That's just between the halfway between EC and EV. Okay, EC and EV. Okay, that's just a EI. That's why EI is banded the same way as EC or EF. Okay, and then if you look at here, there's a lot of extra electrons, right? When we talk about we dope the N side, the electrons stay on conduction band. When you dope the P side, the holes stay on what? Maybe I should plot like this. Not okay. I should plot like a triangle, right? This is how it looks. Uh, as the energy level gets higher, the number of electrons reduces. The hole will be the hole is what? Hole is opposite, right? When the energy level goes lower, the number of holes get less. That's you can think about it this way, right? You have rock in the leg, right? When you throw a log in the leg, the rock sink, okay? But if you have bubbles, right, generate from the bottom of the leg, the bubble flow up, right? That's the same thing, okay? The holes try to flow up, and the electron try to, sink, okay? And then if you have electrons want to go from here to there, since there's barriers here, this much barriers, this is called E barrier, okay? That barriers will be stopped. Okay, the same thing for hole try to go to this side. There's a barrier. This is the same barrier for the hole. That's why you add the bias. Okay, now let's see. If you add the bias to the right side, see here initially this all the states are here. See, EFN is here. Now you move up by QA, QVA, QA you move up. You see now initially this guy over here, right? Now you move up here, QVA, QVA. And then you basically give these electrons high energy. Now they can roll down easily because now their energy is much higher compared to what? Compared to the P side. Like you put a rock on the top of mountains, right? And then it just flow to the to the valley of the mountains. That's it. That's the same concept. Okay. This called forward bias. You basically move the electron on the right side, to even higher, give them more energy so that can flow down to the what? P side. And then reward bias is opposite, right? Instead of you move the rock to the top of mountains, now you dig to the mountains and then you make the valley even deeper. You put the rock there. It's very hard for that rock at the level below the valley, kind of burying the ground for them to go to the top of mountains and flow down to the other side, right? So that's just see this one goes opposite, right? Okay, that's called reward bias. That basically you add the positive side of the battery to the inside. Okay. So Here's another sweet for you guys. Are there any free electrons in persisting wafers, silicon wafers? Because we talk about p-type doping, n-type doping, right? A dope that is a negative charge or positive charge, right? Then the question here: are there any, free electrons in persisting wafers, right? Since a persisting wafer is still a semiconductor, right? A semiconductor under room temperature, there's always so many activated, free electrons, right? So answer here is true because the free electrons will be, 10 power 10 per centimeter square, okay? When you dope it, you typically dope that. If you dope that, right? If you do doping, right? You can improve that to 14 to what? To 10 power 19, okay? Depends how you dope it. You can dope that very, highly doped or, weakly doped, okay? So you do, the answer here is true, okay? And then in n-type, so the question here now, the n-type silicon, which one is the majority carriers? Since we have only 1 hour, we need to cover a lot of information. I'm not going to ask students to answer the questions. Just give you some question here so you can think about it, okay? Think about it. So in n-type silicon, since it's what? N-type dope, negative charge dope. So you have what? Majority carriers is what? It's N, right? It's N-type dope. It's electrons, okay? Electrons. Because N is negative, right? M is negative, okay? M is negative. And then another question here is question asks, the common, electronic devices or display devices. You have solar cells, you have diode. Diode is basically electronic device. Solar cells is a photovoltaic device. Resistor is also electronic device. LED, light emitting diode, that's what? Optoelectronic device, okay? Display devices. So which I is a majority carrier devices? If you think of majority carrier device, that's basically the device use majority carriers, right? If you think about N-type silicon, you use what? You use electrons, okay? If you say P-type silicon, you basically use what? Holes, right? If you use hole in P-type, N-type, electron in N-type, you call majority carriers. If you use opposite, right? Now you see, if you use, hole in the N-type, and then use electron in the P-type, and then you call that, minority carriers, okay? Minority carriers. I hope that's clear, okay? Because you use minority carrier in the devices, right? So as I say, silicon solar cells, because you have N-type silicon, right? N-type silicon, this N-type, I'm sorry, P-type silicon. You have P-type silicon, right? And then you shine the light here. You generate electrons, goes to the top, and then hole goes to the bottom. You basically utilize electron. Now you see electrons in the P-type, and electrons in the P-type, right? This called what? Minority devices. So solar cells minority devices. And then all the diodes, you use majority carrier because you want to move electrons from the N side to the P side, okay? That electron on N side is majority. Transistor is the same thing. You basically use majority carriers to move from the drain to source, right? The source to drain when you apply the gate voltage. LED is the same, right? If you think about LED, if this P, this is the M, PN junction, I'm sorry, the N here on the bottom, I put this. Let me do this P, this M. You basically inject electron to the N side, inject the hole, on the P side, okay? Hole in the P side. You see the hole on the P side, electron on the N side, they are majority carrier. Now they recombine each other, illuminate the light out. That's called display. And then since you use electron on the N side, hole on the P side, that's also called majority carriers. Okay, so here's the answer here, which is following the majority carrier devices. That's what, right? 2, 3, 4, right? All these 2, 3, 4 are majority carrier devices, except solar cells is minority carrier devices. Okay. Here's another question. Probably I think we can talk about these questions, during the Q&A. If I probably leave this question here for you. Maybe I should not talk about it because if we talk about the questions, we don't have time to cover the lectures. Okay. I'm going to skip these questions. Okay, you guys, as a students, you study the lectures, you learn from the class, and then you answer the questions. And then if you have questions, you can come back to me, during the Q&A next 2 hours. Okay. So I'm going to skip these questions so that I can cover the lectures. Okay. So lectures here you can see is the question: solar cells actually under forward bias, but it's minority carrier devices. Okay. So it's clear that because under the sunlight, what you see here, this is solar cells, right? This is solar cells. Okay. Under the sunlight, what you have this, you actually, the sunlight comes here, you promote electrons, right, from here to there, and then these electrons flow to what? To the, from P to M. Now you see electrons initially for diode goes from N to P. Now it's from P to M, right? And then you kind of inject a lot of electron to the N side, and then move this up this much. See here, you move this N side up this much. And then whenever you move this energy level on the N side up, that's called forward bias, right? Because that's the same thing like you add negative of the polarity to what? To the, from the battery to the N side, okay? Whenever you add the negative to the N side, that's called, forward bias. So this forward bias. But the current flow is opposite. Current flow, the electron flow is from P to M. That's why you call minority devices, okay? That's why it's, forward bias, but minority carrier devices for solar cells, okay? So next thing we're going to discuss is the electrical model of our solar cells. So this is very important because typically it's very hard to make a real solar cell, but you can do the very simple simulations because solar cells basically diode, right? What they have, you first have a diode like this, right? You see diode, like this, and then battery or solar cells actually under sunlight you generate the photocurrent, right? That photocurrent is what is here, right? So as we just mentioned, right? The diode electron goes what? Comes from here, from right to left. But solar cells, the electron goes from left to right, right? So now you see the diode current flow and then photovoltaic, photo current flow. The solar cell, the illuminated current flow is opposite, right? That's why when I add a photocurrent, the photocurrent goes opposite direction. See, this electron flow down, but for this, what? For this photocurrent, it goes up. That's why in the real, models, this typically a diode, right? And then if you add this photocurrent, it's just opposite, GPH minus IPH. Okay, the GPH or IPH here, the G is called current density. That's basically the current divided by what? I divided by meter square area. Okay, that's whenever you talk about the current, the ampere per centimeter. Okay, area. Let's see area instead of the unit. Unit is ampere. The unit is ampere per centimeter square. Okay, you call that the current density. Okay, that's the current density. Okay, if you don't divide by the cross section area, that's called the current. Okay, that's the current. The current basically is ampere. Okay, unit is not divided by centimeter square. Okay, so now you see if I think about my diode, that's this equation. If I think about my solar cell, that's this equation. That describes the current flow inside the battery. I'm sorry, inside the photovoltaic devices. Okay. Any question here? If not, let's move to the next slide. So here I think we'll leave this, for you guys to figure out, how to understand this equivalent circuit. Okay. And then next thing I'm going to discuss will be, the Electron Motors. And then typically, in the diode, right? In the diode, you figure what you want to know is that, this diode, this is GIAN, you want to figure out, and then this M, GIAN is called the saturation current, okay? The reverse saturation current. The N, basically you want the N and GIAN, okay? GIAN is called saturation current. That's basically tell you, you can also call that leakage current of the diode, right? Typically, you want the GIAN small because you don't want the diode to leakage anything, right? When it's closed, it's closed. You don't want when it's closed, there's some current flow, right? And then the N is called, ideality factor, okay? Ideality factors, okay? So the N typically is somewhere between 1 to 2, and then GIAN typically as small as possible, okay? That's just what we want to see, a good diode, right? A good solar cells, okay? But the real problem, when you fabricate the solar cells, because the manufacture processing can be different, and then the quality can be different for each batch, for each processing. That's why you need to identify, this N and GIAN, okay? So the way here, if you plot this GV curve, or you call that IV curve, IV curve. That's basically, V is on the X, I will be a what? And OG, not divided by, okay? Not divided by. Or G, IOG will be on the y-axis. And then if you plot this, it's log, log, this is log. This one is regular, V, you call that semi-log plot, okay? Semi-log plot. Because on the y you take log and the x you do not take log. That's the same half, right? Okay, and then with that you can find the m by taking the slope on this side, on the positive side, and then for GIAN, that's a log GIAN. Basically on the negative side you draw a line straight, it's touch here. This tell you the log GIAN, and then the slope here, the reverse of this slope, you will tell you what is m. Okay, so let's see why you can see that. Okay. So this is a GV curve, semi-log GV curve, right? Okay, and this is GIAN, this one minus what? This is minus 1. But since, when talk about on the right side, positive side, since V is positive, and then that's exponential of E. So that can be very big, right? So that you can ignore this minus 1 because that E power V is much bigger. E power, exponential QV over NKPT is much bigger than 1. So you can get rid of 1, ignore 1. Then, this becomes this, then become what? You take log on both sides. This is log GIAN plus this, you see? You can rewrite this. This is log E that get back there, right? Now you see, log GIAN plus V over this guy, right? Over this guy, right? Over this guy, that's a slope, right? That's slope because V over NT, right? This is more like what? Y equal to what? Very simple is Y equal to what? Kx, right? Y plus Kx plus B, right? Kx plus B. So this is B is this guy, right? Then Kx, this basically what? X is V, right? So K is this guy. This is K, right? This is K. Okay. That's why the K is a slope, but it's reverse inverse of slope because that is what on the bottom, right? This is on the denominator. Okay, that's why you can use slope. Okay, so there's a lot of way to figure out that. You can do the same way, and then basically you find one data point. This is G1, this is G2, and then you use this equation G1 equal to this, G2 equal to this, and then G2 over G1 over G2. Then you can get this, right? Then the same thing here, the n will be what? Now the G1 you have what? You have V1. Then G2 you have V2. Now you have G1, V1. You have V1, G1, V2, G2, right? V1, G1, V2, G2. You can find from a plot. And then you use this equation, you can find what? You can find n, okay? So any questions there? So in this quiz, Kb is constant, T is a given temperature, right? Q is constant, and then V1, VB you can find from a plot, GL1, GD you can find plot. They can all find what? Find the ideal entity. Okay. So that's about how to find energy now. Okay. So for this electrical, model of the solar cells, what you can see here, if you understand short circuit, short circuit current density, that's basically you collect this as a wire, there's low load. And then, when you collect this wire, you see the voltage between the, this and this is zero, right? V is zero, right? When V is zero, this V is also zero. So the voltage across the diode is also zero, right? When the diode voltage, gate voltage is zero, you know the diode is closed, right? So now if this is, if I call this here, that's ISC, short circuit current density. And then that's basically what? Oh, current density, right? GSC, right? That's GSC. That's exactly equal to what? Equal to GPH. Because the diode is closed, or the current has to flow this, right? Like that. Doesn't go with diode, okay? That's why short circuit current density equal to GPH equal to GL. If you have load, that's a GL. But there's no load there because it's R is zero, right? And the same thing if you think about the open circuit voltage, okay? Open circuit voltage, right? Let's think about the open circuit voltage here. This is when this is open, right? Then you have VOC here. This is VOC. VOC is significant. And then you see the current flow. There's no current goes here. The current has to flow like this, right? So then if this is the C, okay? This is the VOC. This is also VOC, right? Or this is VOC, right? Then what you see here, that VOC, right? That VOC will be equal to what? VOC equal to V, right? That's VOC is the same thing. Then you can figure out, use this. VOC is 0, right? So here, okay, VOC is V. Now you can find VOC there. Why you can find VOC there? Because the current is 0, right? Look at this. This is G, right? Okay, this is G. And then see here, this is 0, right? Look at this equation, okay? Then because there's no current flow there, that's 0. And then since VOC is pretty big, right? VOC is, on the right side, and get rid of that. And then the GIAN times multiply this guy equal to GPH. From there, you can figure out, that VOC, that's the VOC, right? VOC will equal to what? GPH over GIAN, and then you take a log, right? And then multiply this Q, this part. See this, right? You can figure out that by yourself, okay? So that's basically open circuit voltage. You can use this equation. The short circuit, that's equal to what? The photo current. How much photogelary current? That's the same as the short circuit current, okay? So with that, you can use this equation to figure out what's the GSC. Oh, I'm sorry, what is the VOC, okay? What is the VOC, okay? That's basically, if you know NK, this K, Q, and T, you know that, right? And if you don't know, pattern is given you, okay? And I also give you either IN or GIN. The photocurrent, you can measure that, right? For example, in this example, right? You can find, this probably this is G, right? This is G instead of I. You figure out, you plug this G there, you plug GIN here, and then you plug N equal 1, you plug the T is that, right? T, K is the Boltzmann constant, right? And then Q is elemental charge. You can figure out this, we'll see, okay? That's basically how you figure out that. So answer here, I think is, I have that. Okay, let me see. You can calculate that, I think. A second. So you guys can still see the size, right? So you guys can still see the slides, right? Okay. So here you use this equation, you can figure out, I don't remember which answer, maybe B. You can calculate by yourself, okay? And then, the model, right? We talk about the model. The model can be complicated. That means instead we have one, diode, you can have two diode system, okay? D1, D2, okay? But that's something, if you plot that, so typically you have one curve like this. Maybe I can move this here, okay? And then if you look at here, typically you have, you have one, if you have one diode, you see something like this, and okay. But if two diodes, the slope will be different because you have this D1, there'll be D2, it's like this. So you have one slope for D2, right? Another slope for D1, that's two diodes, okay? That's why two diode system will be one slope, another slope, and then, you go like this, okay? The other side is like this, okay? What you see typically what you see there, okay? So this you can plot it by yourself, use Excel or use MATLAB. It's pretty simple, okay? Now let's talk about, how to calculate the solar cells performance, right? So solar cells typically you have, if you read the solar panels, they have voltage output, right? They have current output, and they have power output, right? These three things, right? So this voltage typically is, rear solar cells. I don't have that here, right? In the rear solar panels, you'll see something like this, right? You'll see, so one square here, another square here, another square here, another square here, right? This is what does a solar panel look like, right? Solar panel look like. If I can show, let me show you solar panels so that you know what I'm talking about, okay? Uh, Go to the solar panel. Okay, I'm going to stop sharing here. Then sharing this, sharing my. You guys see the slides, right? You see the. Okay, let me open. Okay, but this is a not good example. Let me pick another example. Okay, this is a. Okay, can you see this? Can you guys see this? See this? A picture here. You see the solar panels. There's one wafer, second wafer, third wafer. Each of these discs, the disc is actually from the circuit disc, but they cut the side off. The four sides are cut off, right? And then there's still around a lot of round structures here. This is one of these is one wafer. One wafer is one solar cell. Okay, one solar cell have that. If I take a picture of this, copy this to my slides. Okay, I think. Okay, I'm going to stop sharing that one, and then I'm going to share back my slides. Okay. Okay, and then what you see here is this is something I just talked about. Each of these has VOC, has GSC, has this power. Okay, and they have many of these. They can be collected either series or parallel. Okay, depends what is the voltage output you want to have, what is current output you want to have, and then you can collect that. Okay, now let's whatever. So here, this VOC is that when the current is zero. Then when the current is zero, that voltage called VOC, open circuit voltage. Basically here, the low load is open, okay? The GSC is here, or ISC, either GSC or ISC is the same, okay? Because one is current density. And then when the voltage is zero, then that's it, what that. And then you see each of these positions here, right? You have specific I and V, right? You have specific I and V. When then you have this V times I, you get what? You get power, right? Since each position's different V, different I, their what? Their product, their multiplication is different, right? Since their product is different, you find the maximum product, right? When this product, we multiply I is with maximum, you call that P max, or peak, okay? You call that peak voltage, peak power, you call that peak power or maximum power, okay? Maximum power. And then that's the power you output from your solar panels, right? So, okay, so that's it. So basically, what is VOC, what is GSC, and also at that maximum positions, you get what? Maximum power current, maximum power what? Voltage. That's what IM, VM mean. Then PM means maximum power. And then the ISC, VOC, that's the short circuit current conditions, open circuit voltage, okay? Short circuit current, open circuit voltage, right? Another thing is defined as the fear factor, fear factor. Fear factor basically, if I remove all these things here, what is fear factor? Fear factor means, you use the ISC and then the VOC, you get what? You get a triangle. Not triangle, you get a rectangular, right? You get rectangular here. And then from the VM, IM, you also get rectangular. Now you see this one, I use different color, okay? I'm going to use different color here. Okay. You see the areas, the areas there. This one for the small rectangular. And then meanwhile, you can see the big one. This is a big rectangular, right? See the small, the green rectangular area divided by the big red rectangular area. That's the fear factor, okay? So the fear factor basically is what? PM divided by ISC, we'll see that's IM times VM divided by ISC, we'll see, okay? Now, if you get efficiency, because the efficiency is what? PM over P light, right? Pn over P light. See, PS means the sunlight. Okay, IM VM is PM. Then you get this, F fear factor there. This equation you will calculate the efficiency. So now you know what is DLC, what is VOC, what is IM, what is VM, and then what is the fear factor, and then you can calculate the efficiency of your solar panels. Okay. So typically the fear factor for different solar cells is listed here. If you're interested, you can see there. Silicon solar cells are pretty high in the fear factor, and then most of the perovskite also pretty high, and then most of the solar cells has like 70 or 80% fear factor. That's pretty good. Okay, so here is a way for you to calculate the efficiency. I mean, we're not going to do this. This is a question for you to figure out, by yourself. And then next thing probably is important for you to understand the solar cell testing, right? The solar cell testing, what does that mean? How can you figure out this PM? Okay, that's important, right? There are two ways for you to measure or test the solar cell efficiency. One is that you change this resistance, right? See the resistance. Oh, okay. One way you change the voltage. You see here, each of these positions, right? You think about the position I put here. You can change the V, right? The V1 is here, V1, right? Until V1. VOC, right? VOC. And then V2, VN, right? Right? You change this voltage, and then each voltage, when you change it, your current is different. That's where you figure out how you plot the IV, right? Another thing you can see, because whenever each position you have V1, I1, right? I1, I2, then you can get Rn equal to what? And each of that, positions is a Vn over In, right? And then that means the Rn is different for each of IV curve points, right? That's basically if you can change this R, if you change the resistance, you can also measure what? Measure this IV curve. So that's where you test your solar cells IV curve. How you get IV curve? You change your vary your voltage or you vary your resistance, and then you can figure out a plot, and then there you find VI, and then you multiply them together. You can find out the efficiency. Okay, so here shows the equation. I mean, not equation, example, right? You can see which one will give you the maximum power points. Basically, you plot the areas, right? The area, and then you will see which one is maximum, right? Then you can figure out that by yourself, right? Okay, that's also answers the question. You have to track the maximum power point tracker. The tracker is basically do the same way. Okay, there's some question here I'm going to skip. And then you can see here you have three resistance, R1, R2, R3. You can have R1 separately, and then R1 plus R2, and then R1 plus R2 plus R3, right? And then you can also have R2 is there and R3 is there. See here, and then this way you can change what? You change the resistance, and then you find the IV, and then you multiply that IV, you get the power. This way you can find here R1, R1 plus R2, R1 plus R2 plus R3. You can also have R2 itself, R2 and R3, R1 plus R3, R2 plus R3, right? Or R2 itself, R3 itself. And then you will find the curve, and then you can find, you can plot the curve, you can find the maximum power, okay? That's basically the way the industry uses to figure out what is the maximum power point. Once you figure out that, and then you can use that maximum power point as the input to the output, as output to the input for the load, right? So now you know that you have IM, you have VM, right? But your load, right, I air and V air, that may not equal to what? It's not equal to IM, VM. That's why you take IM times VM and PM. And then the PM will be output as a power, right, to your load. And then your load have different IM, VM, right? Just make sure you have IM multiply VM equal to I air over V air, right? So I air, their product will be the same, but I air does not need to be equal to IM. V air does not equal to VM. Okay, that's how you see here. The output is constant, right? The product is constant, but IV can be different, right? That depends on what the load look like. Okay, so this is the tracker, right? So that's what I talk about, right? Typically, you have the solar panels, and then you have DC-DC converters, and then you have maximum power point, and then this output the PM, maximum power to the load, okay? That's it. See, this I is not equal to this I, right? This V here is not equal to that V, okay? That's how you understand how solar cells work, okay? So with that, let's think about uh, the resistance, okay? The resistance. There are two resistance, right? You remember when we talk about beginning the equivalent circuit, right? Model, right? Or electrical model, we just think about here, right? This here and here, right? We don't have this RS, we don't have RSH. So RS here is called series resistance. RSH is called shunt resistance, okay? So basically, nobody can make a low industry, low company can make a perfect solar cells. They always have some losses there. Okay, these losses, that's one is RS series resistance, the other one is a shunt resistance. Okay, if you have recombination in the solar cells, the electron hole recombine with each other, or there's contact, it always has a resistance. Okay, that's why you have RS, RSH. This basically tell you the losses. Okay, so for good solar cells, the RS should be small, right? Because you don't want to, any, uh, current resistance is big. Because if that resistance is big, you have I here, that Vs equal to what? Rs times I, right? But you want that V all comes here. You don't want to have any potential drop at these positions, right? That's why you don't like, you want Rs small. The smaller one is zero, right? Zero is the best. There's no loss there, okay? And then shunt resistance here, you don't want to have any current flow here. That's why it requires what RS should be big, right? When the big is like open, right? There's no current flow, okay? That's why, typically RS should be between, less than 10. RS actually should be big, as high as possible. Should be at least 100, right? Per centimeter square, okay? So that's it. And then now let's take a look at the real solar cells. This is silicon solar cells. What accounts the losses of the shunt series resistance? Basically, in all the contact, see the resistance there, or this contact, the resistance from here to this electron goes from here to there, or the resistance that will give you the series resistance. Now let's see, if you have an electron generator there, there's hole here, electron hole recombine with each other, okay? That's called shunt resistance. Kind of the electron hole, go in between, go inside the devices. They move inside the devices instead of to the load here, okay? That's called shunt resistance, okay? With that, you can do the same thing here. You can, do your own analysis of organic solar cells, dye-sensitized solar cells, or perovskite solar cells. You can do the same analysis. Or the contact provide your series resistance, or the recombination inside the device will give you what? Give you shunt resistance. That's no matter what solar cells, or follow the same mechanisms. Okay, next thing what you want to know would be the equivalent circuit of solar cells. I think we talked about this, right? You have this is the diode, photocurrent, and then shunt resistance, series resistance. Here basically tell you how to plot it, right? How to plot it, basically you analyze the equivalent circuit, right? If you think about the I, this I is equal to what? I air, this I air is the total, current, and then sum goes to ID, right? This ID, right? This one is ID, okay? And then sum goes to what? Goes to the, uh, this, uh, the current, basically you have I air and the I here, ID, ISH. So the total I air minus how much goes to ID, how much goes to it says ISH, right? This ID, right? Then this I goes to the load, right? And then that's a very simple way, right? Total current I air, minus ID minus ISH is equal to I, okay? That's it. That's what you see there, okay? Then, how do you plot it? You can plot it easily, right? See this circuit here, you can modify to this structure on the right, right? And then you can see I here equal to what? If you know this, the total is the V, total from here to here is V, right? And then, here's the VD, from here to here is VD. That's V minus VD divided by RS, and then you know how much current there. That current is the same current as here, right? That's the same, okay? That's equal to what? IPH, right? Elective, right? This, if you think about this is a positive, this is a positive, this positive, and then this this plus this minus that. See here, my current should be go these directions, right? Because my current goes these directions. Then that's a positive, positive minus what? Negative, right? And then that's what you see here. Since you notice V divided by RSH, it's ISH, ISH, ISH. Then this ID minus IPH. And then use this way, now you can be able to plot your curve. Because here, what you need to find out, basically find the VD and I, right? The next slide I'm going to show you here. Right? You find the VD, find I, and then once you know the VD, you see you can find the V, right? You have V. Eventually, you have this to plot your curve, okay? So if you have a question, we can discuss this later, okay? I think 1 hour is pretty short. We need to cover a lot of things. Okay, so here's the short circuit conditions, the same thing, because under short circuit, this kind of collected together, right? Because this short circuit, the voltage is so small here, so VD is so small here that VD can cancel that. So, the photocurrent goes, some goes RS, some goes RSH, right? Since these parallel structures, the current goes to RS, will be what? Will be RSH, right? Will be RSH divided by the total. The total resistance this much, right? And then the voltage will be this guy multiplied by I, right? Now, right? Now this, if you think about how much goes RS, just this divided by RS, right? That's actually ISC, right? That's ISC. ISC equal to what? The total things here divided by what? Sorry, not RS. The resistance, let's get RSH over RS plus RS IPH, right? Since RSH is so high than what? RS. And then this got almost 1, right? That's why it's equal to photocurrent. So short circuit current is almost photocurrent, okay? And then the same thing you can analyze will be open circuit conditions, right? Open circuit conditions, right? Since open circuit, there's no current flow here, you can get rid of this guy, right? So now the current flow, some could dire, some could RSH, okay? And then you can see this IPH, this what is that? This is total, right? Open circuit will be ISH, right? Plus the ID, this IS equal to what? Because this total current some goes to ID, some go to ISH, right? ISH plus ID equal to IZ, right? See this part plus that equal to that, okay? So that's about the shunt resistance, series resistance. When you plot it, you figure out if the series resistance goes up, it always go like this and like this. So this side, closely we'll see it change. For the shunt resistance, it's close to the GSC. I'm sorry, GSC, yeah. Then it goes this side, okay? That's when you plot it, you can figure out that's the way, how this shunt resistance, series resistance will change the IV curve. You can also figure out that from the dark current. So dark current is the same thing, right? Dark current basically, and you will see that when it's elective or small, and this plot, their slope will tell you what is RS. This is a shunt resistance, right? So RSH, okay, RSH. So it's simple. If you analyze this equivalent circuit, since the elective, right? The elective close to 0, the diode is gone, right? Right, and then also dark current is gone because under dark there's no photocurrent. So these two are gone. What you see here is basically this guy. See, okay, this guy. So basically, if you have V here, so this in series collection RSH plus RS. V divided by I equal to RSH plus RS. Since RSH is so big than RS, so that V divided by will be equal to this guy. See that? That's how you get the RSH from the elective or small V. Similar way, you can do the same thing, to figure out, typically this slope here tell you under dark, tell you the series resistance, why? Because under dark, this is gone, right? And also open circuit, right? The current will not flow with RS because the diode is open. See it's here, this is RS plus the diode, right? And then if V divided by I, that's basically RS because here there's almost no what? There's no resistance. The diode when it's open, it's kind of open, right? The resistance almost 0. That's why, it's here. When the V is big, right? The diode is open, and then you get the reverse of this, inverse of this slope. That will be the series resistance, okay? With that, I think under elimination, you can get, here tell you what? Series resistance. Here tell you the shunt resistance. Okay, that's very simple. Okay, I think that's the last slide. Okay. Any question here? I'm not sure. We probably goes over class. Okay, questions? Oh, probably since we have 2 hours, right? We can next 2 hours we can ask questions. The lecture goes pretty fast. Okay.
Thank you, Professor Chow, for such a nice talk on the solar cell basics, and we are very uh, thankful to you. So, I would like to ask the attendees to ask the question if they have any query regarding the solar cell basics explained by Professor Chow.
So I'm sorry, pretty early for you guys, right? Oh no, pretty late. This at night. Okay, last night was pretty early.
No, it's evening. It's 7:30. So it's
7:30. Okay, okay.
yeah.
Is that okay? Mukesh, I think I forgot to CC you in the slides. Just in case if you want to see the slides, uh, Mahesh has all the slides.
Sure, sure, sure. So now I encourage the students to ask the question. I
So
think
we have one
Sayed,
question in the chat
yeah.
box from Dr. Shahjahan. He is asking to please comment on the fill factor.
Oh, fear factor. Okay, that's a good question. Let me go to that slide. Okay, the fear factor. Okay. Okay, I think. Okay, so here's the fear factor. So the question, first, to understand the fear factor, what is fear factor, right? The definition for factor basically, the VM times multiply IM divided by what? VOC multiply GSC, right? That's basically this square, over what? Over this square, right? Over this big square, okay? So that's it. And then for different solid cells is different. But overall, if you have high quality solid cells, you have very small RS, no, very small RS. And I'm sorry, RS, not RSH. And then very high shunt resistance. And then you should have a very high, very high fear factor. Fear factor will be high. It's high. Okay, it's high. But fear factor will never reach 100%, right? Because you always have losses there, right? So the high one, 80%, 85% would be pretty good, okay? And then how do you determine the RS or RSH? And then you go to the slides there, probably I go too fast, Remember here, when we analyze here, we analyze, for silicon solid cell or the contact or the N plus layer, N plus layer be issue, or the electrons has to go through N plus or the hole has to go through P plus to the contact, okay? That N plus will be an issue for us. And also inside the P side, P layer, the P layer, their quality, if you have defect, and then that can cause a very high, very small shunt resistance. That means the electron hole can recombine with each other, kind of the channel for the electron hole go move around inside the devices instead of go outside the devices. So these are the common issues, right? So basically, when you fabricate your solid cells, you want to reduce the recombination inside the devices. You want to improve the crystallinity or the ground boundary issues, and you want to do the preservation of this ground boundary defect, and then you will be able to increase the shunt resistance to prevent the recombination. And the contact or the interface, you also want to have a compact interface, and then that way, you can improve the connectivity of the ITU, improve, clean the substrate pretty well, so get rid of all the defect, and then you have very good, transport for the electron in series side. So, and then the RS series resistance will be small. So these are the basic things typically people, consider them when they fabricate solar cells. Okay, that's the same thing. You can analyze your specific device, either organic solar cells or dye-sensitized solar cells or perovskite solar cells, right? And then you want to have, for example, if this is the Hall transport layer, right, HT Hall transport layer. If this electron transport layer, ET you want to have a very good Hall transport, very good electron transport. Their mobility should be good, right? You don't want them to slow down the electron transport or Hall transport. Then you can have a small RS, right? And then the perovskite, you don't want to have a lot of ground boundaries to trap a lot of electron holes there. Then, you increase the criticality, the quality, also uniformity of the surface of the perovskite. Also, when you grow the perovskite, you want all the precursor to fully grow into the perovskite. You don't want to have this PBI2, TNI2, SNI2, this kind of thing there. Okay, so you also want to get rid of moisture or oxygen, right? Because they can react with perovskite and then form the intermediate state. Okay, so that can also reduce the shunt resistance. So these just examples. Okay, I hope that answers the question. Yeah.
Yes, sir. Thank you, sir. We have another question from Kashif Nazir. He's asking, what is the general range of maximum power for the solar cell?
Uh, so maximum power for the solar cells, is that the question?
Yes, sir.
Okay, so typically, if you think about typically here, if we talk about the power, we also talk about the power, power density. Okay, we call this power, not okay, watt per centimeter, right? Watt per centimeter square, right? If you think about the sunlight, right? The sunlight you get from the sunlight, sunlight you have 100 milliwatt per centimeter square. This typically at noon time, right? Time. At noon time, sunlight is maximum, right? That's about that, right? And then, you know, and then you convert that to electricity. This is a sunlight, right? This is more like a photo, the light energy, right? This is light. And then you convert that to electricity, right? Electricity. This basically times what? 100 milliwatt per centimeter square times the efficiency. Okay, that's efficiency. So the power, maximum power you can get determined by the efficiency for 1 centimeter square. Okay, if you think about 1 centimeter square, each 1 centimeter square, if your efficiency is higher, you have 10%, you convert what to 10 milliwatt per centimeter square. 20% would be 20 milliwatt per centimeter square. If you get 50, it would be 50. So the efficiency determines your maximum power. Okay, and then they come to how to get a high efficiency, and then that will be goes the device structure. Which one first you want to build? What 3-5? Gallium arsenide or doped gallium arsenide, or you want to use silicon, or you want to use a perovskite, and then that will be come to this question: how to make a better solar cells. Did that answer the question?
I hope, sir, he has got his answer. We have few more questions, sir. Let
Okay,
me
yeah,
just
go
go
ahead.
straight. Yeah. We have a question from Himanshu. He's asking, sir, can you please explain again what is the parasitic impedance and how does it affects in the solar cell performance?
Which did he ask the shunt resistance or series resistance?
So that he has not specified.
Okay, so if I go back, look, I can do this one. Okay.
Sir,
If first the students, or you guys can plot your own IV curve. If you look at here, look at this here. This is I, right? This is I, and then this what? This is your VD, VD, right? You can assume my VD is from minus 0.8 to what? Positive 0.7, and then the interval can be 0.1, okay? And then you can plot that by yourself. This IPH, you can assume, anything, right? This just can be a constant, doesn't change IV curve, right? If you think about IV curve, it's something like this, right? Like this, okay? This one is here, right? And then this typically for given solar cell is constant, right? Think about silicon solar cells that can reach what? Like 30 milliampere per centimeter square. But perovskite, they can reach like 20 or 25. Organic solar cell maybe 20 or 17, okay? This is fixed. And then how this, series resistance or shunt resistance change that, you can plot yourself. You can change, you see here, you have what? You have shunt resistance here, right? That's your shunt resistance, right? Then let's see where's the series resistance, right? The series is here, right? The series is here. When you have V, you have the RS. See, when you plot the IV curve, you have RS and RSH, okay? And then you will figure out, when you plot that by yourself, you can figure out that when your series resistance increases, initially my IV curve is like this. Okay, maybe I can, let me start a new slide so I can plot it. Okay. Okay, now I'll talk about the series resistance or series impedance. Okay, all these series resistance, shunt resistance are internal impedance. Okay, so this is V, this is I. Okay, when my RS, for example, I have three. Okay, I have 1, 10, 50. Okay, each of these on centimeter square. Okay, when my RS is 1, I see my IV curve is like this. Okay. Okay, this is my Pmax. Okay, Pmax. PM. Okay. Okay. When my IV curve, when my series resistance increase to 10, my IV curve change like this. See, now Pmax is here. Okay, when my this is 1, RS equal to 1, this RS equal to 10, then my S increase to 50, my IV curve change to this. Now my PM is here. You see how this, oh, I'm sorry. Is there any way I can do it? Do, not undo. Let me replot, sorry. Okay, this is next one is what do you see there? I'm going to show you is you see the IV goes in the inside. That's basically the area, right? See, that's Pmax you have. Keep reducing, right? That Pmax has been go inside, right? Okay. The same way if you do the, now let's do this way. The same way if you do the RSH. Okay, now let's see, I have 1,000 first, right? And then 100, and then goes to 1. The next is 1, okay? The unit is the same thing, okay? I talk about 1 centimeter square devices, okay? And then your IV curve is something like this. Okay, this is the RSH is 1,000, okay? When it reduced to 100, it goes to okay, 100. Then it goes to 1, you go simply a little bit like this, okay? And then you see now Pmax, Max, Max. You see also, this is 1, okay? RSH is 1, okay? That's the 1. RSH is 100, 1,101. You also go internal. You see that? Okay, this one, this one more change on this side. I should keep this side the same. Okay. Ideally, it's
Sir,
yeah,
excuse me, sir.
yeah.
Yes, sir. Sir, is this that parasitic resistance or capacitance which is overall affecting the efficiency of the uh, cell? If we could improve somehow we can reduce the resistance or increase the capacitance. So could we increase the efficiency of the overall solar panels?
Yeah, it is. So overall, this resistance we put here is more like, uh, uh, the numerical numbers, right? But in the real case, how to reduce the RS, increase RSH, that's your fabrication procedures. That's the process, how you fabricate device. Also the materials. You have the materials problem, you have the interface problem, you have contact problem. All these, in order to reduce the impedance for RS, increase impedance for RSH, you have to improve your manufacture process. Also materials selections, yeah. So you are right, yeah.
Sir, you have mentioned in the graph that if we increase the resistance, then the graph will goes upward. Means if we could decrease the resistance, then we get increase maximum power point. Means we would get the maximum power point very soon. So this is maybe the benefit.
Yeah, that's right. So do you what's your question? So what you said is correct, yeah.
Yes, I'm just reiterating your your concept.
Oh, okay, yeah. So because the efficiency, look, the efficiency rate equal to P max, right, over P light, right, or sunlight, P sunlight. Because the sunlight, as I just mentioned, that's fixed, right? Think about the noon, right? It's 100 milliwatt per centimeter square, right? The only thing you increase the P max, right? That P max is higher, and they have a higher watt efficiency. You see that? Because we have only one sun, the sun is same every day, right? I mean, it change a little bit, but overall, the sun give us the same energy, right? So that's why the denominator doesn't change. The only thing you change is the numerator. Numerator is from the P max, right? That's it. Did I answer your question?
Yes, sir. Okay. Thank you very much, sir. Thank you, sir.
No problem. Yeah.
We have one more question from Mr. Niloy. He's asking, how are inorganic and mixed halides peroxides vary in the properties? I mean, he's asking best way to make a stable halide peroxides, like without any inert atmosphere, and what are the possible elements in the future research?
Okay. Yeah. So the perovskite solar cells right now, even people use lead based, but lead can be replaced by other element. Tin is another one, right? There's other or inorganic perovskite materials you can use to replace the lead. So typically, their efficiency is lower compared to lead based. But there's a way to reduce amount of lead. You can have lead, but their percentage, their ratio can be reduced, to a small, very small amount. Okay. There's other ways, you can also increase, develop the better recycling, Then you don't worry about even you use lead, if you can recycle that 100%, you may not worry about that much. Okay, that's about the lead as a toxic element. And then about the stability, about the stability, I think people try to grow what, see right now, when you think about many of these high efficiency perovskite, they use too many elements, the structure too complicated, and then also there's organic, components there. all these can cause the issues. I think the future research will be to minimize the structure complexity, right? Go from, I think we talked about this last night, go from 3D to 2D structures, and then, grow better structures, and then use ore inorganic perovskite, and then that can help to improve the stability. Since there are so many different approaches there, it's very hard to, compare each of them. But this, what I just mentioned, are the major, directions that people try to improve the stability. And the other thing would be the how to prevent the ions diffusion, or ions migration inside the device, especially when the temperature is pretty high. It's not that high, maybe 80 to 100 degree under sunlight, especially in the hot areas, then the ions probably diffuse, migrate pretty. How can we hold these ions there so that they cannot diffuse? Then the ions will not migrate. You will have very stable, morphological, phase, and also very stable, chemical phase inside the devices, and the device should work long, long lifetime. Yeah. So that's what I thought. Yeah.
Thank you, sir. Sir, we'll take one more question before we proceed to the tutorial session. Mr. Saeed, you can ask your question directly.
Hello, I'm audible, sir?
Yeah.
Yes, you are.
Yes, sir. So my question is that, sir, how we can find out the value of the series and shunt resistance from the dark characteristic or the light characteristic of the solar cell?
Okay, that's a good question. All the questions are great. Okay, so here I provide different ways for you to figure out, how to find the shunt resistance, series resistance. So very simple way, any solar cell you make, right? You can measure this IV curve easily, right? See, under this one is under the illumination. Okay, under illumination, what do you need to do? The series resistance is here. Right? This is your series resistance. You can just go these positions, and then you take the slope. When the slope is steep, goes these directions. When the slope goes these directions, you know that your RS increases. You just find the slope. You find the delta V or delta I over delta V, right? And then, you reverse it, right? You inverse this because your I is y-axis, the V is delta, V is x-axis, right? That slope is delta I over delta V. You inverse that, you get that's equal to your series resistance. Similarly, at this, when this one is VOC, okay, VOC positions, okay. This one when the GSC condition V is 0, and then you take this, you take the slope, the same thing. The slope here, here, here. Now you see the slope goes these directions. Then that's the same thing, delta I over delta V. Then take the inverse. That's a very simple way for you to figure out, what is the RS, what is RSH. So this gives you RSH, right? Okay, this is for under illumination. Okay, if you want to do that under dark, that's also similar way, right? Under dark, you take the slope here, close to V0. Okay, this give you what? Shunt resistance, right? And then under dark, if you take a slope close to VOC, see the slope is like this, right? Under dark, you don't have VOC. So basically, when the V is high, right? Then V is high, okay? And then you take this slope, 1 over delta I over delta V. Then that gives you RS. Yeah, did I answer your question?
Yes, sir. Then which method, by using the dark or by using the light, Which is better characteristic to find out the RS and RSH?
So I would say the illumination is better because you basically you want to see the RSH under illumination, right?
Yes.
So the one before is more precise. This one is more precise than the one in the dark.
Okay. Thank you, sir.
Problem, yeah.
Thank you, sir. Now, sir, we have a tutorial session. But I would just like to ask, like, if there is any specific lectures or explanation which you want to give in the tutorial session, or we can continue with the doubts.
Oh, I would say we can continue with Q&A. You know, especially I have some questions there, right? I have some questions in the slides, right? They can ask the questions. They can work out on the problems in the slides, and then ask a question about that. You know, there are different ways because I did not prepare any slides because all my slides is the lecture slides. You know, the student can, you know, ask any question about the slides, or they can answer some questions I have in the slides, you know.
Okay, sir. Meanwhile, while they do that, can we have a few questions which we have left out? Like one question was that how can we increase fill factor in the solar cell?
Oh, the fear factor in solar cells, that's all goes to, you know what? I'm not sure your student has noticed that when I, you know, explain this, you know, when I explain, okay, I'm sorry. Okay, see, when I explain this, I'm not sure if the student has, you know, has pay attention there. See, I have keep this position, no change, right? See here, I did not, this change, you know, but to make simple, you know, ideal case, this does not change that much. See here, right? See, this is VOC, this is a GSC, right? Okay, VOC, GSC, right? So when you change this series resistance, shunt resistance, see here, these two resistance, you know, this Pmax change, right? Pmax goes inside, you know, PM over what? VOC, GSC, right? See, this guy keep reducing, but VOC, GSC does not change, right? The same thing here, right? PM, that's a fear factor. This is a fear factor, right? FF equal to PM divided by VOC times GSC, right? FM. Okay, so from the theoretical point of view, you know, you basically you need to have what? You need to have low RS, higher, you know, RSH, and then you what? Right? And then your fear factor increases, right? Your fear factor increases, okay? This from the theoretical point of view. So from the practical point of view, how can you reduce RS during your device fabrication? How can you increase RSH during your device you know, fabrication? That goes to the same concept, right? You need to have very good, you know, very clean substrate, and then very good, you know, interface between the active materials or electron transport materials, hole transport materials, you know, on the substrate, and then all the interface between active materials and electron transport materials or hole transport materials, you know, and then the active materials qualities, right? Reduce their, you know, shunting, reduce their defect, you know, and then reduce all the impurities, right? For the perovskite, you have to fully convert this precursor into perovskite. You don't want to have any residual solvent, residual, you know, precursors like PBI2 or TinI2, right? Typically, that's called matter X, right? Any, you know, metal chloride or metal bromide, right? You want to get rid of this, right? So that's the way you think about to improve the fear factor, right? It goes from RS, RSH, and then you determine what are the real factors that determine the, you know, RS and RSH, right? That would be device, right? So either contact, interface, all the active materials, qualities. So this is the approach I would take. If my student work, I have student work on these areas. This is where we ask them to figure out, their problem if they get very low fear factors.
Thank you, sir, for such a nice explanation.
Yeah, the fume
Yes, sir.
cycles, right? The cycles of these, whole transport materials, whole transport layer, electron transport layer, the cycle of active layer also determines.
Thank you, sir. We have another question. Like the person is asking, is it compulsory to measure on-off ratio in reverse biased only?
पढ़ाई हो रहा है बेटा, हम आप पढ़ाई करते हैं मतलब डिस्टर्ब करने जाते हैं.
So, can you repeat the question?
Yes, sir. So he's asking, is it compulsory to measure on-off ratio in reverse biased only?
What
So
ratio?
the on-off ratio he's asking.
Oh, can I look at where's the question in the chat?
Yes, sir. It's in the chat box. It's in the chat box, but he has, I mean, message it to me only. Host, let me just type it in the for everyone. We'll see. Now you can see, sir. Just now I have posted it.
Oh, and off. Okay. And off ratio. Can I see the question? Oh, I didn't see the chat. Oh, here. Let me stop sharing here just a second.
Sir, now can you see
Q&A.
in the chat box, sir? In the chat box.
I saw it. Okay. Can we? Okay. On off.
Ratio it is.
Factors are there and possified. Oh, you can, yeah. Oh, you basically you want to add bias there. You measure the IV curve. Is that the question? Is that the question you want to add bias when you measure the IV curve under illumination? Is that what it means on off because you add bias or don't add bias? So typically we, because we do a lot of solar cell research, but we seldom do this, we seldom add the bias because the solar cells works under sunlight. When it works on sunlight, it has its own bias, right? That own bias is actually we'll see, right? Open circuit voltage or VM. That VM, maximum power point voltage, that's the bias it adds by itself because the sunlight shine on that and then it adds bias. That's how the solar panel works. So that's why we never add extra bias to the solar cells. So that's why I got a little bit confused with the question. Is that the question you asked? When we measure the IV curve under the sunlight, can we add bias there? Or, photodetector is the same thing. The photodetector is different, because photodetector, you only measure the current. Photodetector basically works under what? Under this short circuit current conditions, because you want to measure how many photons and then you know how many electrons there. So you don't care about the power, you don't care about the voltage actually.
So I hope
Sir, actually, when we have to focus the light on the device, so during that time, we have to provide the electric bias.
No, you do not need to provide electric bias. That's when you do the IV curve, you provide the electric bias because you do not have load there, right? You want to add a load there. That load, as I mentioned earlier, you can add the load. You can also just tune their bias. That's the bias you tune it. It's not the bias you add it. It's kind of you add it because you have to tune it, the bias, You have to tune it to that, because you don't know where's the PM, right? That's why you tune the V there. It's kind of you add the bias. But that bias for the real solar cell under sunlight is not because you add bias there. It's because you have the load there, the load. And then you have maximum power points tracker that tunes the voltage. You can see that's the add bias, but it's not exactly, it's not actually the add bias. It's the bias that generated from the solar bias there. Just because you don't know where you want to find out that, you tune it that way. Did I answer your question?
Yes, sir. But when we have to measure the any responsivity or like that any transit response, so we have to like that. If we put that 0 volt, it will be self power. If we provide a negative bias or should positive bias should be working there
Uh, can
during
you repeat
transit
the
response.
question?
If we measure the
Can you
transit
repeat?
response
Yeah,
of that device,
yeah.
so we have to provide some voltage. Either we have to provide 0 volt or should provide positive
Yeah, yeah,
voltage
yeah.
or should negative voltage. So if we like that in photo detector condition, some people are doing in the negative bias or some are representing in the positive bias.
Okay, got it. Okay. So typically a photo detector, you can use either positive or negative. That's fine. Uh, because if you think about the IV curve there, once it's reached, the GSC there is pretty flat, right? The GSC go to negative or go to positive, they're very flat, right? So that in that point of view, you can add either, positive bias, the forward bias or reverse bias. That's fine, right? But when you add this reverse bias, you need to be careful. You don't add the reverse bias too big, right? You see the IV curve when it's reached to what? VOC or higher. When it's past the PM, and then that current will be different, right? So it's very hard for you to correlate that with the real, number of photons if you talk about photo detector. But here, since we talk about solar cells, we care about the power. We care about the I times V, right? So that V, even if you add the bias there, basically you don't want to see you add the bias. The solar cell has to work because you add bias. That bias is actually the bias is generated by itself. You just want to figure out where it is. That's why you tune it. You adjust it. You know what I mean?
Yes.
Yeah. So the real solar cells does not need to work have under a bias you apply. That's because it has the bias there. You need to find out where is it. That's why you modify it. You know what I mean? That's why we see solar cells works under forward bias, right? Forward bias, but the current flow is opposite. So I know it's very confusing, right? You think about when you measure the IV curve, you have to apply the bias, right? It's actually you tune the bias. You tune it from small to bigger, and then you want to figure out where's the maximum power point. That's it, you know. But it's confusing. I understand you. Yeah.
Okay, sir. Thank you, sir.
So we have another question. Can you see in the chat box from Ankit? Uh, he's asking to
Yeah.
comment on the voltage in the dark current term, especially its origin.
Okay. Okay. So the dark current, now we talk about dark current, right? The dark current basically is the diode. That's a diode, okay? So this probably, when you talk about the dark current, that's the bias you have to add. Under the dark, there's no photovoltaic. There's no photocurrent, right? All the current is response from the diode, right? So that voltage is not photovoltaic. It's a bias, right? This probably is a very good question connected to the question asked earlier. This bias is real bias now. And especially close to the origin because you add the bias there, okay? You add the bias. And then our assumption is that, the shunt resistance, series resistance will not change either, between the dark and under illumination. That's why, we can measure that RSH under dark as well. So I mean, did I answer the question? So the word you ask here in the dark, that's the bias you add. Okay, that's the real bias you add. Yeah.
Sir, in solar cell case, we don't have any biasing. So, what is that V that I want to ask?
Oh, which one? You mean the
Uh,
dark? Why you add bias?
in solar cell case, we don't have any biasing, right? So what is that V in dark current term that I want to ask?
Oh, okay. So in the dark, right? In the dark, basically it's a diode, right? You add bias and then the current flow, right? If you don't add bias, there's no current flow, right? So you have to add the bias, right? But under solar cells, that is not the bias added because the photo generate that QVA, right? Let's go back to the slides, okay? Let me show you the slides, okay? Just a second. Like keep this. Let me keep this, okay? And okay, you see the slides here. Can you guys see the slides?
Yes, sir.
Yes, sir.
Okay, you see this one is photocurrent, right? This is photocurrent, right? See, this under dark, this is gone, right? There's nothing here, right? So the bias at here is only flow through what? The diode, right? You see this? You see that? So in the dark, you have to add bias, right? Because there's no photocurrent. There's no photocurrent, right? There's no photocurrent, there's no photovoltaic, right? The photovoltaic is also gone. Everything comes from the bias added, right? That's basically diode, right? You see that? So in dark is real bias, right? But under the illumination is very different, right? Now let's go back to the. I know this is pretty confusing, not only to you guys, to many people are confused by this. Okay, now let's go to. You see this one? Okay, this is a great slide. You see, this forward bias, right? Look at this forward bias, right? This one is a diode, right? This diode, right? With no light. Okay, low light, right? This is no light, right? Here is what? No bias under light. You guys see the difference? The same thing, the same solar cells, right? This no light under forward bias, that can happen the same thing. No bias under the light, right? See, when you talk about bias, people talk about the bias. The bias can be what? From the photo bias, right? One photo bias. That's what solar cell does, right? Second one is what? Electric bias, right? You add what? You add bias like the forward bias diode, right? The third one can be what? Magnetic bias. But typically for solar cells, we talk about photo bias or electric bias, right? See, now solar cells works, real solar cell works under the light bias, not the electric bias. But the light bias, electric bias is the same thing, right? You know what I mean? You can have a bias there without light. You can have bias under light without the electric bias. Okay, this is low, not bias. Okay, low electrical bias. Okay, this should be low electrical bias. Okay. So now, because typically people talk about bias, it's talk about electrical bias, right? Low electrical bias. Now I think I answered the question. Did I answer the question now? Maybe for both the student and student before this. Is that clear for you guys?
Yes, sir. Thank you.
Okay. So the dark one is actually on the left side, right? Low light, but under electrical bias. Okay. I should add another word here so that makes it clear. Okay. So this is good. This shows that you guys are thinking. Okay. No light,
Yes, sir.
but under what? Electrical bias. No light bias, but electrical bias. Yeah, you have electric bias but no light. Here is no electric bias but under light bias. Okay. That's it. Okay. Good.
So we have one question in the question and answer section, but I guess you have already answered it. Like he's asking, what are the different parameters to reduce series resistance and increase shunt resistance?
or the parameters. That's basically the yeah. I think we answered that question. You know, when you think about first, you need to know what device you are dealing with, right? If you are dealing with polymer solar cells, or dealing with silicon solar cell, dealing with perovskite solar cells, all these parameters will be different. But in the common thing between them, the interface, right? The materials quality, the recommendation between inside the devices, right? So that's basically the things you consider, and then your question will go to what device you are working, Then we can think about, specific for specific devices, what action you will take to reduce the increase shunt resistance, reduce series resistance. Yeah. So do you think we should take a break, like a 10 minutes or 20 minutes break, right?
Yes, sir, we can, sir. So,
Yeah.
so participants, we are taking 10 minutes break. So if you guys, we have already shared the material with you of both the lectures. And if you guys have any question, you can please type it in the chat box. We'll ask after 10 minutes, right?
Okay, great. So we'll be back like my time will be 10 o'clock, right?
Yes, sir. I
Okay,
don't,
great, great.
yeah. Okay. Hi, sir. So we have one or two more questions, as you can see in the chat box.
Okay.
Importance of tunnel effect on the solar cells performance.
The chat box. What I see here is
Ashok Kumar has asked the question. Okay, he has asked me, sir. Let me just post
okay,
it for
okay,
everyone. Just wait a second.
no problem. P substrate parameters. Can I get a clarification of the question? You talk about the dopant concentrations or the thickness, or what is the question?
Sir, let me just unmute him.
Yeah.
Ashok, you can ask your question.
Sir, what is the if we see in the PN junction we have see the effect of the tunneling effect. So if we in our device any effect of the performance of the device of tunneling, like PN junction we see that tunneling effect have more response current and then.
So you ask the question about the PN junction, right? The
No,
PN
no, sir,
junction,
like
the
that.
P,
If our solar cell have a PN junction type structure and so we how can the tunneling effect affect the performance of that solar cell or device if there is a tunneling effect in the device?
or tunneling, okay? The tunneling effect, okay?
Yeah.
So okay, so the tunneling effect, you talk about the tunneling effect, right? You talk about the I mean electron. Are you talking about the okay? We were talking about this probably in chapter lecture 5 or 6. We'll talk about PN junction, and then we'll talk about the mechanism. How how this recombination, inside the PN junction, and then what is the built-in potential field, and then uh, also later we'll talk about the tunneling that we want to use in the multi-junction devices. The tunneling, between this junction, next junction, there'll be P plus, N plus, how they will recombine the devices. So there are two concepts. The first concept in the single junction, PN junction, we do not want the tunneling to happen because the tunneling can kill the devices. The tunneling, the higher tunneling, the higher recombination, you will have a higher saturation, I mean, reverse saturation current, that GIAN. You see that diode, there's a GIAN there. When you have very high, possibility for tunneling or very high possibility for recombination, that GIAN will be big. That big GIAN is not something we want, okay? But in the multi-junction devices, we do want to see this junction and then the next junction. We want to see the tunneling here that kills the extra, charge inside the devices. So, so the short answer here, for single junction devices, we don't want to have any tunneling there. But for multi-junction device, we do have tunneling, especially for the central junction, because the central junction, the charge cannot be get out of the charge cannot get out of the solar circuit. So we want that charge to be recombined. So I'm not sure if I answered the question because the question here is pretty big. It's pretty general.
Ashok, sir is asking something. So I guess he's facing some network issue.
Okay.
Professor Chao, I have one query.
Yeah. Yeah.
Uh, if we talk about this structure of solar cell, like planar solar cell layer by layer, heterojunction and bulk heterojunction. So,
Yeah.
and dye sensitized solar cell. Among these solar cells, which solar cell have perfect ratio of this RS by RHS? to say
Oh, okay.
low parasitic losses are in which solar cell, and what is this junction between material is playing role? Like we are if we talk about bulk heterojunction or heterojunction solar cell or planar solar cell, so which one will provide this low parasitic losses?
So uh, so typically, when we compare the solar cells, we do not compare, Dyson style solar cells with perovskite solar cells, right? We only compare the inside the Dyson style solar cells, uh, if your solar cell does not function well, we figure out what's the reason there, right? Because the materials are different, the interface are different, your substrate are different. It's very hard to compare, like a bar heterojunction. Can you guys see the slides here, or you don't see? Did I share anything or not? Let me share the slides here.
No, sir, we cannot see.
Okay, so you see here. You see
Yes,
here
sir.
is,
Not yes.
I have three different, solar cell structures, right? The organic solar cells and then perovskite solar cells are very similar, right? Even perovskite solar cells originate from the Dyson solar cells. When people were developing the solid state, whole transport materials, right? People use polymers, and then people realize perovskite can be whole transport materials. Then that's how the perovskite solar cells was originated. Then they figure out the perovskite cell can absorb the sunlight, can convert, sunlight into electricity. And then they change the, mass perovskite to what? I'm sorry, mass TiO2 into this compact TiO2, right? That's how all the story come out, right? And then, so nowadays the perovskite is not like, Dyson style solar cell. The perovskite solar cell structure is very like what? Organic solar cells, right? It's also very like PIN, organic solar cell, like amorphous silicon solar cell, right? That's what we see nowadays, right? So, so now come back to the question, if you think about uh, the fear factor, I think I showed earlier, right? Typically, the fear factor is a good indication about the shunt resistance, series resistance. You think about, they are all similar, right? PSSC, organic, perovskite. Perovskite silicon is a higher, you know, but overall they are comparable, right? So from this point of view, there's no big difference about the RSH between different solar cells. It's more like for the same type of solar cells, when you fabricate that, the idea, the logic here can help you to identify to understand why that happens and then how you can improve it.
Okay, yes.
So that's what that's my thought. Yeah.
Sir, I want to know that the maximum fill factor we are getting like 0.855. So is there any way to maximize the fill factor so we can get the maximum efficiency of solar cell?
Well, so I think there's possibility you can get 0.9, but it will be really hard to get even higher than 0.9 because I think thermodynamically you cannot reach 100%. You always have lost it somewhere. So I mean, theoretically it can be reached to what? One, right? 100%. But I mean, practically you cannot make it happen, because you cannot have perfect interface, you cannot make a perfect, resistance. There's no resistance there. That just doesn't happen. So that's why, as high as possible, if you have a given systems, right, or given, device systems, there may be some modeling can tell you. But generally speaking, there's no theoretically maximum, fear factor. That's it. That's what we see now in the academic or industry.
Sir, one more question. Is the fill factor or the performance of solar cell is may vary on like this perovskite, and very few solar cells like organic, these are not industrialized, commercialized right now, as per my knowledge, maybe.
Yeah, yeah.
So there is any change in performance due to this fabrication process involved? Because like we talk perovskite solar cells, so right now I have gone through few papers. So they have processed the solar cell using sol gel processes.
Yeah. So if I understand your question right, you're asking, you know, the efficiency in net best would be different from I mean, the commercialized, manufacture process. Is that your question?
Yes, sir.
Okay. Yeah, you're right. So right now, many of these, except silicon solar cells, right, that can be, mass produced. There's fabrication lines there. Everything has been optimized so well. But for perovskite, and other like dye-synthesized solar cells, organic solar cells, there's no real production lines there. I mean, even there are some pilot, right? Like a pilot, production line, but they have not been matured or optimized so that can produce very high reproducibility. So with that point of view, there's one issue. For example, whenever we talk about this, we have two use example, right? Think about the perovskite solar cells. You can make small areas like zero point 0.2 centimeter square. The efficiency can be very high, but when you think about 1 centimeter square or even bigger, the efficiency always drops. Or even you get some good efficiency, but you cannot make a consistent result, or you cannot have very high, very good reproducibility. Right? So these are the engineering problems, right? Application. How can you make a large scale solution based processing that can have very uniform cyclics, very uniform, morphologies, very uniform grain boundaries. That can be a big problem, right? It's different from silicon. Silicon, you make the wafers, right, and then you cut the wafers, right? So that's easy, right? You make a good ingot and then you cut the wafers. That's it. It's fixed, right? The single crystalline silicon, this everything is the same, right? But for perovskite is the polycrystalline materials, under different temperatures and different, solution concentrations, you add different additive and then they are different. That's why I produce too much, uh, too much factors or too much, things for you to generalize or, process, because standard process is so difficult. So that's why that can bring the, challenge for the commercialization for the mass production. So that's true. Why is that? It's not easy to scale up. You can scale up easily, but how can you control the quality for the processing? That'd be the challenge. And then how to scale up from the lab-based small areas to big areas. Yeah.
So the professor, जो fill factor you have described here is only for this lab scale area like 0.2 mm square or like this.
See again.
So fill factor you have shown here like for this DSSC perovskite solar cell and
Oh,
this organic solar cell.
this is they typically consider good, fear factor. I mean, if you make a very poor devices, you can have 0.1, 0.2, You know what I mean?
So when
It's
we
just
move,
acceptable if fear factor. Common, people report it. A good
okay,
one, right? There's always bad devices you can get 0.01, I mean 0.1, 0.4, 0.3. All these are possible.
yes, sir, it is always there.
Yeah.
So, sir, when we scale up this perovskite, when we increase the area of solar cell for
Yeah.
any solar cell, like we have done it for zero point 0.2 mm square, or if we are going for higher area, so the fill factor will get changed due to some losses when we increase the area of solar cell.
Yeah. That's the same thing, right? For example, for the small devices, you can control the, very uniform morphology. You can control the pinholes, right? You can control a lot of things there. When it gets bigger, if you can control the uniformity, right? The pinholes, as you control for the small areas, you'll be fine. You should get similar, fear factor. Not just because of it get bigger, everything change. When you get bigger, you have to control the same quality. That's the challenge. For the mass production.
So I think that is the only reason for the popularization of this silicon-based solar cell, because the uniformity is very well maintained.
Yeah, you're right. Yeah,
Well, thank you so much.
no problem. Yeah.
Yeah, hello, sir.
Yes.
Sir, regarding that the N naught and N and J naught, so it is a very useful parameter for analyzing the performance of any solar cell. So, what are the parameters which affect this N and J naught, and how we can improve this value for the device performance?
What do you mean energy now?
No,
Say
no,
again.
no. Yes, see, the saturation current and the N.
Okay, okay, I see. You go back to the okay
Yes, yes, I'm looking
here,
for.
right? And
Yes,
okay, okay, this you talk about this.
yes,
Okay.
yes, sir, yes, sir. So sometimes in the reverse bias, in the negative bias, we are not getting exact straight line like that. Some increment is also found in some device characteristic of the solar cell, dark
Okay.
as well as in the light characteristic. So how we can analyze that device characteristic that this J naught is affecting, or some how it is affecting the device performance. Like this is ideally the in the negative bias, the J naught is throughout the constant, but in some practical device in our lab, we are not seeing the constant in the reverse bias. So what are
Okay.
the factors basically this that are affecting?
Okay. Good. So can I know what device you are using in your lab?
Yeah, and generally I'm trying for the zinc oxide on silicon solar cell, zinc oxide silicon heterojunction solar cell.
Oh, zinc oxide. Okay. Okay. I see. Okay. Good. So basically, let me go to the future. I have some slides in the future talk about this. Just a second. Let's see. We can pull that slide out. Some of these questions actually, goes way beyond. So right
Yes,
now
yes,
we basically
yes,
introduce very basic concept, right? But these questions
yes.
goes deeper.
Okay, okay, sir. Then maybe we'll
Yeah,
discuss
just,
in
just
the
a second.
coming,
I
sir.
can pull the future slides out, and then we can, since this is discussion, right? We can discuss anything. I think let me go to the p-n junctions, okay? And then, okay, so if I go to, let me share you new slides, okay? Many of the questions you guys ask, that will be discussed later, okay? Let's see. Here, stop sharing and then new slides. Okay, now I show these slides will be chapter, we're discussing chapter 6, 7, and 5, 6, and 7, probably chapter 5. When we talk about that kind of. And then if you see here, who is talking there? Someone asked questions or somebody did not unmute mute themselves. And anyway, so look at here, right? You talk about the GS, right? GIAN, right? See the GIAN? GIAN will be, think about regular p-n junction silicon solar cell, right? Fed by Ni square, Ni square, and then the Dn, Na, Ln, dp is basically, the majority carriers, At the in the acceptor side, majority carriers on N side, daughter side on the acceptor side, and then the carrier diffusion length, the carrier diffusion coefficient. You see this? We'll talk about this in the next, maybe after a few days. And then that explain what is the GIAN look like. They determine your GIAN. Now, since you form silicon zinc oxide, right? So that what your silicon? Your silicon is N-type or P-type silicon. And then your zinc oxide, what is, did you dope the zinc oxide? Can I know more information there?
Yes, sir. We are using P-type silicon.
Okay, and then the N-type zinc oxide, right?
Yes, yes.
So yeah, then what basically you think about all the PN junction will be similar. You have N-type silicon, P-type silicon, or you can use P-type silicon, other type of N-type materials. The PN junction will be similar, right? And then this is basically this tell you what is GIAN. If you think about the specific, how this diode will be formed, how the depletion region will be formed in that PN junction. So that can be very complicated. There's no single answer, to just explain it. So once you know your device structures, and then basically you want to have a lower GIAN, right? You talk about that GIAN, you talk about saturation current is not flat. That's basically because you have the shunting there. You have shunting, as there's different bias, especially it goes negative bias. You just suppose the ideal case that all the charge on the inside cannot go to the P side, right? But now since you have shunting there, you have tunneling there, there's charge flows there. There's electron hole recognized there. That's why under different bias, this, the tunneling happens more significant. And then that's why you see the current flow. There are current flows there. There should be blocked, but now there's some current flow in that reverse bias. That's why that's what you see there. That's either from the so interface has a defect or there's tunneling spots between the zinc oxide and the P-type silicon. You look at the band structure, you can study that. See, now since I don't know what the band structure look like, it's very hard for me to just speak from knowns. So I hope that answers the question.
Yeah, okay. Thank you, sir.
Okay, no problem. Yeah.
Sumit, you wanted to ask something?
Yes, sir. I have questions, sir. What type of nanomaterials are best, or what materials have so far achieved the best efficiency in case of dye synthesized solar cell?
For Dyson solar cells, I did not track the current progress for Dyson solar cells maybe for quite a few years because now I shift my focus too much on the perovskite and lithium batteries. That's it. So Dyson solar cells, if you think about, you say nanomaterials, I assume you talk about the anode, right? The oxide. Is that the question? Because if you think about regular Dyson solar cell, you have diode attached to the TiO2, right? So did you ask a question about the TiO2 nanoparticles or nanomaterials? Is that your question? Because I want to get clarification from your question.
Actually, I have not idea about more, but I have question. So I have asked you.
Oh, that okay. So so if you ask about the Dyson solar cell, what is the best nanoparticles? That's still the titanium dioxide. That gives the best performance. I mean, people have tried zinc oxide, have tried other kind of oxide. Also try to dope zinc oxide and then dope other type of oxide. But the best performance still from the titanium dioxide. I mean, that comes the first time. I mean, rather use the Dyson cells about 1991, a long time ago, right? So I would say the best one, if you think about just anode, photoanode side, that's still titanium dioxide, best. The efficiency probably 14% or 15% for Dyson solar cells.
Okay, sir. Thank you.
Yeah, hello, sir.
Yeah.
Yeah, basically my question regarding to that the modeling of the solar cell. So suppose we have the dark and IV characteristic of the solar cell. So for the different, by varying the different parameters through the fabrication. So by using the two diode model, basically we are getting the two J0, two saturation current density J01 and J02. And so from that, how we will analyze the performance of the device that and
Okay, so let's see. I see here. Okay, so so typically we talk about the. I think you asked question again goes to the future slide. If you look at this slide, right, we have specific discussion about a D1, D2, two diode. One diode would be the just happens inside the special charge regions. That's the depletion region, p-n junction. The other diode goes actually to either p side or n side, and then that's basically diffusion limited. Okay, so one will be the diffusion, the other one will be recombination based. Okay, so this is something we'll discuss probably Wednesday or Thursday. When we talk about when we're discussing this. So that's basically you think about the two diodes. You first need to understand the mechanism, the physical mechanism, right? What are the real D1, D2 mean, right? When you understand that, you will know, uh, how to analyze this specifically your devices. But without the physics behind, we cannot understand anything about D1, D2. So we have to link that with the physical process. Either one, diode will happens inside the p-n junction. The other one may happens outside the p-n junction. Okay. Even inside the p-n junction, you have recombination. You can have a diffusion, right? You can have drift, right? Which one dominate? Typically, you don't have both of them at the same time. Otherwise, you'll be confused. The device will not function well. You will have one dominate, and then that one dominate. That special regions. Which one? What is the diode look like, right? And then if you go to P side or N side, so here why we for the regular p-n junction solar cells, why we said the D1 is on P side, because P side has much thicker thickness, right? If you think about the structure, the N plus P plus, right? The N plus probably what 500 nanometers. The P is about 500 micrometers. And P
yes,
plus
yes.
about, the 400 or 300 nanometers. Because that P is so thick, we have to consider the diffusion can be limiting parameters. That's why we have a diode assigned to that. So yeah, so this just give you idea that, when you analyze this D1, D2, you have to, consider the real, device structures, the real, mechanism for the charge transport, and then you have D1, D2 there. Otherwise, you will not have D1, D2. You have only one D there, one diode there. Yeah. So that's
So
my answer. Yeah. Yeah. Go ahead.
and so for analyzing this is basically available in the bulk type solar cell, or is it also can be analyzed for the thin film based solar cell by using two diode model, or one diode model is sufficient for the thin film solar cell?
Oh, this okay. This depends your solar cells. If you think about thin solar cells, if you see the IV curve, especially in the seminar, there's two slope. You have two diodes there. If you
Okay.
don't see it too slow, you have one diode there. So that depends. You can easily tell from your IV curve.
Sometimes say in the light IV characteristic, we are seeing the two slopes. So one is in the in between the JSC and VOC, and when it is the current is positive, then it is giving different slope in the light IV characteristics. So what we can conclude from that?
Oh, that one, many times is not the diode, that's many times because of you have huge defect, huge transport problems. And then that problems is associated with the bias, not the bias I'm talking about. That bias is the photogenerated bias, right? And the different bias that transport For example, the diffusion and just example here, D1, D2, right? The D1, D2 also determined by the p-type materials quality, okay? Then also the p-n junction quality, right? So the same thing for you. If you see the two slopes there under the illumination, but you don't see the two slope under the dark, and then that may tell you, just because you have huge defect, something there, that can slow down this charge transport in that range of the bias, in that range of this, the voltage, and then, that doesn't mean your entire device has a two diode resistance, but since that defect that caused that issue, it look like a two diode system.
Yeah, but in the dark IV characteristic, we are not seeing this type of behavior, but it is generally available in the light IV characteristic.
Yeah, so that's what I say. Maybe the photo-induced defect, the photo-induced, most probably for you under the illumination, because you have some defect, you have some problem in the devices, you have accumulation of the charge inside the devices. And then that changes the electric field distribution inside the devices. That's why you see the curve kind of, look like two diode, look like two diode there. You know what I mean there? Because
Yes,
you
yes,
generate a lot of photo charge there. The photo charge is accumulated inside the devices, and then
yes.
you generate a local electric field. That causes the issues there.
This
That's
may be
yeah.
this may be due to the interface problem, or it is a bulk defect will affecting more there in this situation.
Oh, yeah. That's a possibility. So that one, uh, you know, I don't know. I don't know what device you have, what the structures, and then is it NIP or PN, or how 6N, how 6P, what is interface? Did you do any interface modification? So this is very complicated. For me, because I have no idea what that look like, so I can only speak from the general point of view.
Yes, yes. Okay, sir.
Sir, I guess we are done with question and answers.
Okay, great.
So, yes, sir. So I personally have one question, which I wanted to ask out of curiosity. Like, sir, I had attended one conference few years back on renewable energy, right? In which one of the Japanese automakers were showing the vehicle on which there was a printed solar cell, right? So I just wanted to ask, like, is it like a near future, or is it still in the, I mean, processing stage for the like self-sustainable vehicle models or something related to that?
Oh, so can you repeat your question? I kind of got lost with your question. You talk about the
Okay.
printing?
Yeah, for printed solar cells, sir. Actually,
Yeah, print.
those
What kind of solar
yes.
cells? Is any solar cells or just I mean, printed, right? You can use printing to make Dyson solar cells, perovskite solar cells, organic solar cells, even amorphic solar cells. There's possibilities there. So so you talk about the general printing solar cells, or a specific type of solar cells?
No, sir, they had only demonstrated like printed solar cells. They have the concept of printing it over the vehicle roof and make it kind of self-sustainable running model. Like it should run on the electricity what it produced from the solar.
Okay.
So I was
So
just, yeah, I was just asking like, is it a near future which you'll see, or is it still in the processing stage?
okay, this one, the printing, I would see, so nowadays you talk about the additive, manufacture is hot, right? So people talk about 3D printing, I don't know this printing you talk about, is that 3D printing? The 3D printing, since it can print anything, can even, Tesla tried to print their car, right? And then printing can be used to, print anything, manufacture anything. So that can be a trend, but I don't know how soon that will come, you know.
Maybe, sir, in near future. Thank you, sir.
Yeah. There's possibility in
Yeah.
the near future, even now they use 3D to print electronic circuit, right? I mean the IC, right? Integrated circuit, so you don't need to go through this microelectronic fabrication, right? But nowadays, still the best device to generate from there, right? So from the
Yes.
traditional microelectronic fabrications, right? You still need to use lithography, right? This lithography help you to reach very small definition, very small resolutions, right?
Yeah, because there are some problems with the conventional solar cells. I mean, they are heavy, they are not bendable. So with the printed one, we have that flexibility, so we can print it on the regular. Yeah,
Right.
yeah,
So
so
I
that
agree.
would be
It has a very very high potential, very high possibility to be successful.
yes, sir. Yes, sir. Thank you, sir. With this, may I request Professor Mukesh Kumar, Professor Mukesh, sir.
Yeah. So it's a great session actually. So a lot of question. Student really enjoyed. So Professor Chow, can I ask one question?
Yeah, sure. Go
Okay,
ahead,
so
Mohan.
it's a lot of research actually is going on. It's kind of saturated for perovskite. So is there any like a parallel scientific community is taking any parallel path for new materials, or is still a lot of energy is going in this stability of this perovskite?
Now if you talk about these are the materials development, and then the way to address the stability issues, they are coupled with each other, right? Basically, a lot of this instability comes from the materials, right? So people do spend a lot of time, developing new materials that can be robust, can be stable for perovskite solar cells.
Yeah.
And meanwhile, a lot of research goes to the pilot manufacturer, that can be a new field, right? If you can, get some funding to develop the scale up, that'd be good, because right now is a perfect time for people think about how to jump into commercialization effort earlier. If you jump earlier, you get resources, right? You can develop technology faster than others, right? That's why there are a lot of startup companies, in the perovskite solar cells as well. So I have to see from the fundamental side, you're right, the materials development, the materials discover important to address the instability, right? And the device structures or the material structures goes to 2D, right? And then on the manufacturer side, how to manufacture the perovskite solar cells at large scale, maintain their reproducibility, high rate of successful devices. That's a lot of areas.
Okay. Thank you very much. So as there is no question, so thank you very much, Professor Chow. And we will start in the morning again in Indian Standard Time at 7:30.
Okay, great.
Yeah, thank you very much.
Mukesh. Thank you,
Thank you.
Mahesh. Also, thank you, Ahmed and huh?
Thank you, sir.
So
Thank you so
I
much, sir.
see. Okay, great. So this you have this host, right? The GAN courses. What's your name?
Sir Nipun Sharma.
Okay, you are
Nippon.
Nippon Sharma. Oh, you have a
Yes.
larger name here. Okay, great.
Yes.
Thank you, Nippon. Okay, great.
Thank you, sir. Thank you, sir.
Bye. Yeah, we'll see you
Bye,
evening.
Yes, sir.
Tomorrow morning for you guys.
Yeah.
Yes.
For us, it will be morning, sir.
Thank you, Professor Chow.